All right, welcome everyone. Last class of the semester. Today, is our kind of free-for-all for a final exam review. So you can really ask any questions that you'd like. Again, I want to encourage folks to not necessarily choose the hardest question out there, possibly. Just because it'll take me a long time to go over it, and it may not be especially relevant for a timed assessment. And so I'll try to gently push back, but really this is a kind of a free-for-all, so you're driving. Quick few administrative announcements before we jump into the math. Posted a kind of what we dream the schedule should look like for finals week. Certainly you'll be taking your final exam on Monday morning. And then we're hoping to have all the finals and makeups and everything kind of graded and the course grades computed and all that sort of stuff by Wednesday at 1. So we plan to release the final exam grades along with the final course grades by Wednesday at 1. And then our goal is to submit to the university. They have a pretty fast turnaround time as well, but our goal is to submit to them by Thursday at 1. So that's kind of what the order of operations looks like post-final exam. So for your information, we have a post-course survey that's due tonight. So if you haven't done that yet, set an alarm or something. We can't give any extensions on that because the semester will be over and all that. We've talked about this in Monday's class and Wednesday's class, but I feel like we should at least showcase this one last time. Again, the final exam is cumulative. The final exam you don't take in your regular room, either this room or your recitation room, right? You need to go to your MSU course schedule, or we've compiled them all into one document, but you need to know what section you're in or who your TA is, whatnot, and to figure out where you're going to take your final exam. Similar to the midterm, you'll be provided a formula sheet. You can bring a calculator and pencil and all that sort of stuff, but you can't use notes or technology. There are various good things that you can be doing to study. I recommend lots of study. And with that, I think that's everything that I really wanted to make sure that I covered. Any questions about any administrative stuff in the course before we jump into the math? Okay. So then, math it is. Let me go ahead and pull up here fresh sheet of paper. And typically, I would say that there are usually enough questions that it's rare for me to call on the same person twice. So, if you get a chance to ask a question, please make sure it's your favorite question, the one that's maybe most pressing or most interesting for you to get answered. Of course, we will continue to run Piazza and all this sort of stuff over the weekend. And so if you do have additional questions that don't get answered here, you can certainly ask there as well. Okay, and with that, who would like to kick us off with the first question? Yeah, up here.
So I'd like to divide together on the second derivative test of Lagrange multipliers.
So, okay, you've asked two separate things. So you get to choose one. What do you like more, Lagrange multipliers or second derivative test stuff? Second derivative test stuff. Okay, so the second derivative test, this came up in 14.7. This is when we were talking about mins and maxes. So in particular, we had 2 days for this. And the second derivative test was necessary for finding local mins and maxes. As you go back and you review and you look at and you think about for absolute mins and maxes, you'll notice that you never use the second derivative test. So for absolute mins and maxes, of course, you need to know what your critical points are. Those get added to your list of potential absolute mins and maxes. And you need to check your boundary, and that takes a while, right? But you never use a second derivative test. And so, yeah, the second derivative test comes in when you're talking about local mins and maxes. And for local mins and maxes, you're interested in, well, first you need to have some critical points. So let's suppose that f of a, b is a critical point. And we'll say it's a relatively nice critical point. The only ones that you can really apply the second derivative test to are where the x derivative and the y derivative are both equal to 0. If one of these is undefined, you would technically get a critical point, but you couldn't apply the second derivative test because if the first derivative is undefined, the second derivative has to be undefined as well. So you don't really have hope of being able to apply this test. So, right, you usually solve a system of equations. You figure out when these are equal to 0. That gives you a critical point. And then when you have a critical point, right, then you're interested in classifying this. And this is where the second derivative test comes into play, right? So the second derivative test talks about some determinant of a Hessian matrix. So this determinant, we'll say f sub xx, f sub yy, f sub xy, and because these are usually nice functions and whatnot, Clairaut's theorem is in play, and I'll just write this. And so we have, once we do our determinant, we have something like this. And I don't know, I'm going to try to resist the urge to just rewrite out the entire second derivative test and all of its conclusions. This is on your formula sheet. So this is important for you to know, right, that you can look up on your formula sheet. I mean, certainly you need to know when to apply it. And so that's why I kind of emphasize the fact that what this is used for, right? It's used for classifying local mins and maxes. But when you actually go and you're trying to figure out, okay, what are the conditions that make this a local min? Or what are the conditions that make this a saddle point? Or what are the conditions that make this a local max, right? These are well spelled out on a formula sheet. And so I maybe don't need to go over kind of when the determinant here is positive, you're either going to have, right, a min or a max. And then you use the regular old Calc 1 second derivative test to determine which one it is. If the determinant here is negative, you get a saddle point, and if the determinant is 0, it's inconclusive. Again, all of this is kind of well spelled out on the formula sheet. So I'd say this is my kind of decent overview about the second derivative test, what it gets used for, and most importantly, where you can find it, right? Does anyone have maybe a specific question that they're interested in seeing that maybe has to do with local mins and maxes, just to kind of finish up this topic? Because I gave theory, but no example here. Okay, well, fair enough. We can always come back to this as well, but it's dangerous to make up an example because if I try to make up an example, it's one of these things that I can very easily miss the Goldilocks zone, right? I can very easily make something that's completely ridiculous, right? Because I have to solve a system of equations here, right? And so I can make something that's completely trivial, in which case you'll say, this wasn't at the right level for the final exam or for an exam in our class. This is way too easy. Or I could make one that could absolutely kill us, right? And it would take the entire class period. So, I mean, these things need to be well constructed. Did you happen to have one?
FXX.
Huh?
Can you use FYY instead?
So the question was, so in the rules, it talks about if the determinant is greater than 0 and the second derivative, both with respect to x, is greater than 0, then remember you have something that's concave up. So f of AB would be a local min. And then there's something very similar, and it talks about f sub xx less than 0, in which case it's concave down, and so you're going to have a local max. And the question was about this f sub xx here, is this important, or can you use f sub yy instead? Technically, you can use f sub yy. I would resist the urge to try to confuse the graders. Right? I mean, our textbook and kind of all of our web work homeworks and everything was all built around the textbook and this f sub xx stuff. Technically, you can use f sub yy, and you can find this out in the proof, and I think I mentioned it in class. Rather than f sub xx, they always give the same sign if you're in this case where the determinant is greater than 0. So yes, you can use f sub yy, but I can't think of any scenario where there's an advantage to doing that. And the only thing that it can possibly lead to is confusing the graders and getting temporarily marked down, right? Because once you realize you were marked down and you can ask about it, right, you will say, okay, yeah, you're right. But you could confuse the graders and accidentally get temporarily marked down. So, all right, well, that's probably enough for now anyway, about the local mins and maxes and the second derivative test. why don't we transition and talk about something else? So another question, yeah, back here. Mhm. Yep. So the question, as I heard it, was about line integrals. And we saw two flavors of line integrals in 16.2. So this was 16.2, if you want to see more of these sorts of questions. We saw some that where they look like this. So you have some interesting curve, and you're adding up a scalar function. Why don't I go ahead and, so an example of this would be, let's say xy ds, right? It's a function that outputs scalars, right? So once you feed it an x and a y coordinate, it's going to output things like 5 and 13 and -12 and things like this, right? Versus there were situations and there were many different ways that we could denote this. I think in class, right, there was like 5 different ways that you can denote line integrals over vector fields. And the one that you had mentioned was f.dr, which is a nice clean looking one. So I appreciate that. But there are other ways that this can be denoted. And maybe an example of this would be if you had, again, you're going to have a vector field here. So I'm going to say xy comma 2x dot dr. So, I mean, I could spend a lot of time talking about these differences and whatnot, but what it comes down to is this first one here. You're adding up some scalar quantity. The example that I gave, right, was we're a whale swimming around and we're eating up plankton. So if you had some plankton density function as your f, your little f here, right, you could add up and those would be scalars, right? It doesn't make sense to say a vector amount of plankton, right? So a scalar amount of plankton at each spot, right? There's so much plankton and we add that up as we swim around, right? So this is one thing that you can get out of this quantity here. The main application for line integrals with vector fields is going to be work. So we calculate out how much work the vector field has done in pushing some particles along the curve. So you're getting different quantities, and yes, I mean, when you go and you actually do the calculations, right, this ds is different than this dr, right? And so you have to be careful on what you put there. Did I answer anything close to your question? Yeah, okay, good. Because I feel like this subject is, especially, I can just kind of ramble and there's lots of alleyways that you can visit. So any other questions about line integrals and these differences here before we move on to another topic? Anyone have a specific line integral problem that they would like to see done out? Okay, fair enough. Why don't we go ahead? Another topic. What other questions or topics would you like to discuss? Stokes theory. Okay, what about Stokes theory do you want to talk about? When am I going to apply Stokes theorem? So, all right, so Stokes theorem. Came up in 16.8. And so let's start with the question that I heard is, when are you going to apply Stokes theorem? So the number one time that I'm going to apply Stokes theorem is if the problem says so. So we want to get these out of the way. The low-hanging fruit we get out of the way. So the problem says so. So if it says a bunch of other stuff, but use Stokes theorem, right? Then, of course, we have to apply Stokes theorem to this, right? And Stokes theorem is the fact that these two quantities are equal to one another. And so Stokes theorem says that if you're interested in calculating out the surface integral of the curl of the flux of some vector field here, that this is equivalent to doing the line integral. And so if the problem tells you we want to calculate out this quantity here using Stokes theorem, Well, I mean, first of all, you could just calculate this out without using Stokes' theorem. I mean, we know how to do the curl. We know how to do surface integrals. We know how to do all these things, but calculating out this quantity hasn't then used Stokes' theorem. Stokes' theorem is the fact that these two things are equal to one another. And so if we want to use Stokes' theorem, well, then we need to go across to the other side here, and we need to then calculate out the line integral. And likewise, if it asks you to calculate out this line integral by using Stokes' theorem, again, we know how to calculate out line integrals from 16.2 and 16.4 and 16.3 and all these sorts of things, right? We've had plenty of practice calculating out line integrals, but those don't use Stokes' theorem, right? Using Stokes' theorem means that you have to go across the equal sign and then calculate out with this other quantity. And so that's the big thing when it says use Stokes' theorem, really do use it. Don't just calculate, like we did in 16.2, but actually use Stokes' theorem. So that's the first thing. The second thing, when would I use Stokes' theorem? If I see this quantity, curl of f dot ds, this doesn't really come up so much, right, with a lot of the other surface integral stuff. Most of the time, when I see this, when I see a surface integral, it's just f dot ds, right? And we calculate this out. And we did that a lot in 16.7. We did that in 16.9, where we used the divergence theorem, right? So all of these things, whether if it's a 16.7 or a 16.9 style question, you're just going to have flux. You're not going to have the flux of the curl, right? There's not going to be a curl in sight, right? And so if it says, hey, calculate out this quantity for me here, you can choose to use Stokes' theorem, right? We can choose to use Stokes' theorem and then trade that in for the other side, right? Even if it doesn't say that you have to, right? This is certainly a possibility. So if I saw this quantity, this curl of f dot ds in our surface integral, I'd at least have it in the back of my mind that, hey, Stokes' theorem is a possibility, and it may be quite reasonable. The third type is going to be the hardest to maybe identify. And so you may even get pushback from fellow faculty members and stuff like this if this was to be proposed for a final exam question. But it's when you have a line integral, you're given something like this, but maybe the line integral would need to be parametrized in many pieces. So we saw this in a class dedicated to Stokes' theorem. So you kind of had an idea that we were going to be using Stokes' theorem. But if it doesn't tell you, hey, use Stokes' theorem, and it just gives you a line integral, something like this, that is made up of many pieces. So in this case, if I wanted to evaluate out this line integral, there are 4 different line segments here that I would need to go around in order to evaluate this line integral. Each one has its own parameterization, r. Each one you would need to calculate out this dr thing by taking derivatives, and then you need to calculate out the work done on each little piece, right? With Stokes' theorem, you get to trade this in for the surface integral. And in general, the surface integral is more difficult, but it's only one surface integral. So instead of having to do 4 different line integrals, you could do this with just one surface integral by appending this surface, just by kind of shading in this nice flat plane here, which probably has a nice normal vector and things like this. But this one seems quite difficult to maybe ask students to do on the final exam, I would say. But those are the times when I would use Stokes' theorem. Sound good? Anyone have any questions about this or a specific Stokes' theorem problem that you'd like to see done out? Yeah?
Is there going, because Stokes' theorem is the generalization of Green's theorem. Are
Yes.
there still cases where we want to use specifically Green's theorem over Stokes' theorem?
So yeah, the question was, because Stokes comes from Green's theorem, are there situations where we would still want to use Green's theorem over using Stokes' theorem? And I would say yes, just because Green's theorem is so much easier than Stokes' theorem, right? You don't have this curl and all of this extra stuff. You don't have to worry about your normal vectors and orientation of surfaces and things like this, right? I mean, with Green's theorem, the fact that you're just kind of down in 2 dimensions, a lot of this stuff vastly simplifies. And so although technically you don't have to use Green's theorem, you could basically always use Stokes' theorem in its place. And of course, I'm talking about the circulation version of Green's theorem currently. Green's theorem, it is easier. And so although it doesn't work in every scenario, of course, that Stokes' theorem works in, kind of the speed and the time savings may be worthwhile to you to not completely forget about Green's theorem. So yeah, I would say it's worthwhile to recall. So again, Green's theorem really quick. Just this was 16.4, and it talks about another way to trade in a line integral with a vector field. Now this, again, you need to be in the XY plane. So this vector field here can only have P's and Q's, right? 2 components, rather than this one up here would have 3 components typically, P's, Q's, and R's. In this case, you get what? Q sub X minus P sub Y dA over the region inside. This is the kth component of curl, and your normal vector, because you're in the XY plane, would be 0, 0, 1, right? AKA K. So basically, this is just kind of simplifying down curl dot your ds. You would get that exact quantity there. So again, they are consistent with one another, and Stokes' theorem does kind of deal with more situations, but Green's theorem, I think, is a little bit faster if you have this in your mind as well. We'll go here and then here, okay? Yeah. Sure. So a linearization type problem. And then I guess if you wouldn't mind, maybe if you have a favorite one, those ones aren't as dangerous to make up on the spot. So I suspect I could do a fairly decent job, but just if you have one, that's great. Okay. Say negative 0.2. Yeah. All right. So I guess just try to make the jumping around minimally. Did you have a question about the Green's theorem thing before we transition topics?
The right hand, the right hand to know to counterclockwise and clockwise. I'm not sure how you do this. You know, you using right hand to know how to do the.
Yeah. So maybe I can quickly draw out here. So with this orientation that we have for our curve, it's kind of counterclockwise as I'm viewing at it right now, right? So if I was to use the right-hand rule, basically, the fingers need to follow the curve orientation. So in this case, going around like this, and the thumb points in the direction of the corresponding normal vector. So if I was to do this kind of relatively nice one, fingers are rotating around. Maybe I'll draw it to here for the folks watching the video and whatnot. My fingers in my right-hand rule are following the orientation of the curve. And then my thumb, again, for my right hand, is going to be pointing upward, right? So this is a way to determine which normal vector corresponds to this orientation. If I was to draw the same sort of picture here, but now have our curve go around in the opposite direction, something like this, then no matter how I try, right, my fingers for my right hand, they need to go like, blue again. They need to go in the same direction as the curve here. So my thumb can't be pointing up. There's no way I can really do this. I have to turn my right hand over in order to get my fingers to follow, and in which case my thumb is pointing down, right? So in this case, the normal vector would be pointing down. So when you're trying to figure out which normal vector you're interested in, given the curve's orientation, right, it follows this right-hand rule. This one, you'd be interested in the normal vector pointing up, right? And the second one, you want it pointing down. Yeah? Yeah, for 3 dimensions.
This another direction while you're looking at that orientation will be totally different, right? Like if you're looking from XY plane and you change from YZ plane, and the orientation will be different, right?
So the orientation from viewpoint, the words that you would use to describe it, it's true that those change, but the right-hand rule wouldn't change, right? I mean, if we imagine, so this table right here, suppose is the surface, right? And depending on whether I'm looking at it from above, right here, or if I'm looking at it below, right? If we have the orientation for the boundary of the surface going in this direction, right? Still, my right hand has to follow this. And whether I'm looking from below or above, right? Still, the right-hand rule would give the same result, even though the ways that you would describe the orientation change. Yep. All right. So, to linearization. Linearization, FYI, came up first in 14.4. It was the main application of tangent planes. So it's the same sort of thing as in Calculus 1, where we use a tangent line to approximate a function, maybe a complicated function. So long as you're relatively nearby, the tangent line can approximate the function quite well to wherever you're pinning the tangent line. And likewise, for our three-dimensional situation, right, same sort of deal, but now you're using tangent planes rather than tangent lines. So when it says a linearization and that we're going to use to approximate, really, this is the same thing as the tangent plane. So there are different names that essentially mean the same thing, right? So we want to find the tangent plane. Now, the tangent plane equation, I think we've had several of them, but this is the one that I'll write down here. Of running out of room. So here's our tangent plane equation. And you can notice that we need, this is an application of our partial derivatives. So we need to know what our partial derivatives are. And all of this is happening, right? We need to pin our tangent plane to a point of interest. So in this case, we're interested in finding the linear approximation, aka the tangent plane, at 0, 0. So those x naughts and y naughts, right, are going to be 0, 0. So x naught, y naught is the point of interest. We're interested in pinning our tangent plane to the surface at 0, 0. So we can start to plug in some of that stuff. But it doesn't tell us what z sub 0 is, right? Z sub 0 should be the corresponding z value. And this you usually get by just plugging into the function, right? So we know our x and y coordinate, our point of interest. We plug those in, and when I do, we get the f value. The output here would be 3, right? So 0 plus 3 divided by 0 plus 1. So this z naught then is equal to the function's value at that point of interest, at that x naught, y naught, which in this case, right, we saw was 3 divided by 1, 3. So we can start to plug in some of this information. Z minus 3 is equal to f sub x at 0, 0 times x plus f sub y at 0, 0 times y. This is essentially all of the stuff that we can do without any calculus, right? Now we need to start taking those partial derivatives. So we can go back, and I'll probably copy paste here just so I don't have to keep on jumping up and down and what have you. So here's our function. I'm going to go ahead and first figure out the partial derivative of this thing with respect to x. And I'll just do it the safest way possible. You don't technically have to use the quotient rule here because only your numerator has x's. So there is a faster way to do this. But if I'm trying to think about one way that works all of the time, right? For a problem like this, I'll just use the quotient rule, even though it's a little bit of overkill. And so we'll take the derivative of the top times the bottom minus the top times the derivative of the bottom, and again, with respect to x. So the derivative of the bottom with respect to x is 0 here, all divided by our bottom squared. So there's going to be a little bit, well, anything times 0 is just going to be 0. And so you're going to have this 4y plus 1. You have 1 on top and you have 2 on bottom. And so this is just going to be 2 divided by 4y plus 1. And so if I wanted to plug in my point of interest, 0 for x, 0 for y, I'm going to get 2. So this coefficient up here that I'm interested in is just going to be a 2. All right, next up, derivative with respect to y. So again, you don't technically need to use the quotient rule here, but it works. So I'll do that. So we have the derivative of the top with respect to y times the bottom minus the top times the derivative of the bottom, again with respect to y, all divided by our bottom squared. So in this case, what? We have -4 times this 2x plus 3. We don't have nearly as much nice simplification as we did before. But that's okay. We're still going to plug in 0, 0, and that should get us some nice simplified answer here. So when I plug in 0 for x, let's see, I'm going to have -4 times 3. That's going to be -12 on top. And when I plug in 0 for y, I'm going to have 1 squared on bottom, aka 1. So this just ends up being -12. So where we are so far, we have z minus 3 is equal to 2x minus 12y. That's the first place where I have my full tangent plane equation, right? If it asked for an equation for the tangent plane, I could just stop here, right? But we want to actually do something with this. We would like to use our tangent plane to approximate the function's value or the output if I was to give it some other number that's near 0, 0. So in this case, I want to know what is the output if I gave this thing 0.1 comma -0.2. And so since we're looking for the output, it probably makes the most sense to solve this z equals, right? Z is going to be our set of outputs. So I'm going to go ahead and write this as z equals 2x minus 12y plus 3. And if I was to go ahead and plug in 0.1 comma -0.2, let's see, I'd get 2 times 0.1, -12 times -0.2. And so let's see, this is 0.2, this is plus 2.4 plus 3, so this is going to be what, 5.6. So the function's value is approximately 5.6, which we know from the equation of the tangent plane. Any questions on this one here? No? All right, you have a new topic then? Yeah. Okay, yeah. So the question is about flux and some of the keyword I don't know, descriptors that you can use for the orientation of flux. So flux, again, is one of these key words, and flux first shows up in 16.7. So if you're interested in finding more problems about flux, you go back to your 16.7 webwork homework or in the textbook or what have you. But flux means a surface integral with a vector field. This right here is notation. It's common notation. It's kind of like the notation for line integrals, right? We had like many different ways that you could denote line integrals. But this right here is notation. And really, if you wanted to be a little bit more explicit about your calculation, it's f dot n and then a non-bold ds here. And I only bring this up because orientation is all about choosing your normal vector, choosing your normal vector to be a certain desired direction. So that n there is the normal vector. And when you choose the orientation, it's essentially choosing this normal vector to have some property. And so like you mentioned, you could talk about like upward flux. Or likewise, you could talk about downward flux. And so if I was to choose, let's have some surface here. I'll do my best to kind of copy it, whatnot. So this has a set of normal vectors to this surface, and we would want the one that is pointing maybe upward. So again, it needs to be normal, so it needs to be at a 90-degree angle sort of deal. But we want the one that is pointing upward, aka it has a positive z component to it. Likewise, if you were asked to calculate out the downward flux, instead of choosing that one, right, you would choose the one that, again, 90 degrees to it, but it has a downward z component. And z components are nice just because you have these kind of nice descriptors with them, right, upward and downward. But you could also say, find a flux with that has a positive y component, or a negative x component, or something like this. So I mean, with z, you just get to say upward, but you could also choose orientations with respect to x or with respect to y, in which case you would just say that has a positive y component or something like this. So you could do these other x's and y's rather than just z, but z is somehow nice. You can also talk about if you have a closed surface, or something that you could at least imagine is closed, and I'm drawing something that's kind of a sphere here, then you could talk about outward flux, aka has an outward orientation, or inward flux, aka something that has a inward orientation. Your normal vector points inward. So these really make sense when you have a closed surface. Sometimes you can do a little bit of an abuse here of notation or of this phrasing here. If you have something that's kind of, you can imagine could be closed, so here's a elliptical paraboloid, something like this. I have seen it, even though, again, it's kind of an abuse, right, to say outward versus inward here. So something that points outward versus something that points inward, just because you can kind of imagine it's a cup, right? And kind of, if you say outside the cup and inside the cup, that does make sense to us, at least in the English language. And so even though it's not a completely closed surface, it does kind of make sense to talk about inward and outward flux here as well. So again, outward flux, you have to be careful because there's not kind of a nice, mathematical inequality or statement that you can make that what is outward flux. You really have to draw the picture, draw the normal vector on a test point, and figure out if it's pointing outward or inward, right? Because if I have a vector, and let's suppose that the vector is, 0, 0, 1. So that is, it's not moving at all in the x or the y direction, 0, 0. And then it has a positive z component. So, and again, we want it to be normal, so it should be perpendicular somewhere, right? So we would look at this and say, great, that's pointing outward. And I have it up here, this is outward flux. But on the other hand, if you had 0, 0, 1, and if you were down here, right? Well, now that's pointing inward, right? So the fact that any one component is positive or negative or anything like this cannot dictate to you whether you have a outward or an inward pointing normal vector. You really need to know where you are on your surface. And so for these ones, right, you can't just write down a quick mathematical inequality or something like that we could with upward flux. Upward flux is just z is positive, right? But for inward and outward, you really have to take a test point and figure out kind of where you are. So like inward flux would be pointing to the inside of the sphere, right? But again, you kind of need to know what your normal vector is and where you are on the surface. So you can't just write down a quick statement. And likewise, I guess I'll shade these in purple, right? Outward, do something like that, or inward, going into our cup, into our elliptical paraboloid. So those are some of the common phrasings that you get for the various types of flux. Any questions on this here? Yeah?
Going off that, you said the equation for that is f dot ds.
Mhm.
Does that mean you can always use divergence theorem on that?
No. So the question was, because we're calculating out f dot ds, can you always use the divergence theorem on that? And unfortunately, the divergence theorem, like many of our theorems, have hypotheses to them, right? And the big hypothesis for the divergence theorem is similar to Green's theorem in that you need to have a closed surface, right? You need to completely surround some 3D region. So like this first one that I did kind of like a squiggly plane, there's no 3D region that this completely surrounds. So there's no way that we could use the divergence theorem on this. When I drew the sphere, yes, you could use the divergence theorem on that because it does completely surround some 3D region. And so you could do the triple integral of that 3D region that you've completely surrounded. And then in the third one where I have this kind of elliptical paraboloid, this cup here, again, it doesn't completely surround. If you had the cap as well, if you had the top, then it does completely surround. But if you just have the elliptical paraboloid, the cup itself, and it's open on top, then it doesn't completely surround, and so you can't use the divergence theorem. So yeah, the divergence theorem, you really need it to completely surround. Question about this? Okay. So yeah, the question is when you're using divergence theorem, you don't have to worry about outward or inward or things like this. Divergence theorem is like Green's theorem in that you assume that you're calculating with a positive orientation. And so the problem, and we saw this in our class notes and whatnot as well, that if the problem does not specify to you the orientation, you take the natural orientation, right? So, and you saw actually, an instructor was talking to me about our web work problems and whatnot. And I think like of 16.7, when we were talking about flux integrals, something like 3 out of like 5 or 6 of them don't specify the orientation, right? Because you're then assuming the positive orientation. So you've already done this, is what I'm trying to tell you, is that this is not like a new thing that I'm springing on you guys. You have already done this. So the natural orientations are like if you have inward or outward, right? It's going to be outward, right? And this comes from divergence. When we calculated this in 16.5, right? Divergence, when stuff's expanding away from the point, right? When you have your vector field pointing away, right? That's positive divergence. So that hence the positive orientation when it goes outward, right? Versus when you come inward, right? If you're compressing at a point versus expanding at the point, right? If you're compressing, then that the divergence is negative. And so the inward, right, kind of corresponds to the negative orientation. And of course, then we had that definition of that word incompressible, right, in 16.5, if the divergence was equal to 0, right, if they had balance. So yeah, if you're calculating out using the divergence theorem, you're calculating out outward flux. If the problem wants you to calculate out inward flux, it's fine. You can calculate outward flux. You can do all that work. Suppose you get the answer of 5. Then what would your inward flux answer be? -5, right? So it's just whatever the outward flux is. If you want to alter your orientation, you incur a negative sign. I see 2 questions back here, and then we'll come around up front as well. But why don't we start here and then go here, okay? So yeah, the question is, if you're on a sphere, how do you find out where the normal vector would be? So you're going to be choosing a test point, and you need to use that test point for 2 things. So the first thing that you need that test point for is where are you on the sphere? So let's suppose that I say that we have this a nice sphere here, and we have I'm going to choose the test point 0, 0, 1, right? So I know that I'm at the North Pole. So the question is the normal vector at the North Pole pointing upward or downward, right? So a quick way to do this, right? Let me write down a few more specifics here. So x squared plus y squared plus z squared is equal to 1. A normal vector for this we can get from the gradient. And again, when you're choosing an orientation, right, there's quite often in a lot of these Stokes theorem problems and surface integral problems and whatnot, our normal vectors have pluses and minuses that we can choose, right? Outward versus inward, or upward versus downward, or all these sorts of things. So I'll include the plus minus here. But then we choose a test point. And like I said, we need to choose a test point on the sphere. And I'll choose the test point 0, 0, 1, so I know where I'm at. And when I plug that into my normal vector, we get 0, 0, 2. And again, I can choose my orientation with that plus minus. So if I like 0, 0, 2, I'm just going to leave it as is. and choose the plus here because that's not going to do anything. But if I want to change my orientation, I'm going to choose the negative here because then when I distribute that through, right, then I'm going to have 0, 0, -2, right? So if I wanted that, I could do that. But 0, 0, 2, right, is an upward pointing normal vector. And so if I was interested in an outward orientation, I'd be completely content with this choice for our normal vector. And if I wanted an inward pointing normal vector, of course, then I would choose the negative. So, yeah, you really need to know where you are on the surface, and you do that with a test point. And you take that same test point and you plug it in to the normal vector equation to figure out what the normal vector then would look like. Okay, and then right next to you, I think you had a question? I think so, yeah. Any last questions about Flux and this stuff here before we move on? Yeah?
Like, the elliptical paraboloid,
Huh?
could you technically do divergence theorem for it if you take the unit between the surface and the cap and then you subtract the flux from the cap?
Yeah, there are clever ways to apply the divergence theorem where you pretend that it's closed and then you account for your sins or whatever. You account for your error, right? So yeah, there's a clever way that you could do it, but I'm not sure if that would be the most time friendly. I'm not sure. Yeah, it really would depend on the problem. I'd probably say just calculate it on the flux in the normal 16.7 way is almost certainly going to be faster, but maybe you could come up with a counterexample. So, okay, with that, we're happy to transition away from Flux. Yes. Yeah. So maximum rate of change when you're given a function. So this comes when we were talking about rates of change. This had to do with directional derivatives. So this comes up in 14.6, and you were interested in max rate of change. And so before we talk about the maximum rate of change, we should talk about, well, what does it mean rate of change, right? So rate of change in 14.6, we were talking about surfaces. And so maybe I'll draw some interesting surface. And maybe we're at a point, right? And the rate of change is how much does the surface increase or decrease depending on which direction that you look in, right? Because if you're standing on the side of a hill, some directions, you can imagine they're going to take you down the hill. Some directions are going to take you up the hill. Some directions aren't going to, I mean, maybe you can kind of go in this direction and stay at the exact same height or something like that, right? So there are lots of directions that you can head in. And depending on where you're looking, you may get a very small rate of change, or you may get a very large rate of change. Sorry, question about this? So the question is, doesn't this involve a tangent plane? Yes, it's certainly related to a tangent plane, and you can make connections. But in this section, we didn't really do that so much. So ultimately, and I'll spoil the surprise a little bit, this has everything to do with the gradient, right? So the gradient is going to give you the direction in which you have the maximum rate of change. So this direction here in my silly picture, as I've drawn it, I think this would be about in the direction of the gradient. This is where the maximum rate of change would happen. So this is the direction at which the maximum rate of change occurs. Rate of change occurs. And then if you wanted to know, well, what is that maximum rate of change, right? How much do I increase as I take a step in that direction, right? That has to do with the magnitude of the gradient. So if you're asked to calculate out what is the maximum rate of change, it's the magnitude of the gradient. Now back to your point, the gradient, as we saw back here, kind of shows up. I mean, we were talking about on some f of x, y, the gradient is just a partial derivative with respect to x and a partial derivative with respect to y, right? So that gradient, that ends up being these components of our normal vector here that go next to the x and the y here. So yes, the gradient is certainly related. And if you found the maximum rate of change, instead of doing the surface itself, but if you found the maximum rate of change of the tangent plane, you would end up with the exact same answers. So they are all very friendly with each other. But technically, I mean, you can hold them in two separate hands, and the maximum rate of change you can think about just as something to do with a gradient. And you don't need to know really stuff about tangent planes and what have you in order to calculate that out, although you're following a pretty similar path. Does this answer your question? Any follow-up? Huh? That's exactly right. Yeah. Yep. So if we had a specific point, let's suppose it's 2, 1 or something like that, we'd find the gradient, plug in 2, 1. That would tell us the direction that you're interested in, excuse me. If you wanted to know what actually was the maximum rate of change, then yeah, you would take the magnitude of that, and that would give you the correct answer there. All right. Good. Well, yeah, it is 2:40. I see you guys are packing up and whatnot, so that's probably a good place to end. I will stick around if you have any quick one-on-one questions. Otherwise, I wish you all the best in studying for the final exam, and I hope everyone does really well. And yeah, it's been a pleasure, everyone. So thank you very much.
Do you know how many questions it would